Hello friends, welcome to Physics Online. I am Sudhir Vaidya and today we'll be looking at electrical dipole. So let's begin. So what's electrical dipole? As you can see over here, electrical dipole is a system of two charges of same magnitude but opposite in nature. That is, one is negative, one is positive, separated by a fixed distance. An example of a dipole in molecular sense is water molecule. If you look at a water molecule, then one side of the molecule has a concentration of positive charge and one end of it has concentration of negative charge. Both are equal, so the molecule per se is neutral, but then it acts like a dipole because there is a positive charge and negative charge equal in magnitude, separated by a distance. So system of two charges equal in magnitude but opposite in polarity, that means the sign, separated by a fixed distance, is called an electrical dipole. Now we look at another thing that is called as the electrical dipole moment. So a vector quantity associated with the electrical dipole whose magnitude is equal to the product of the quantity of electrical charge and the distance between the charge and acting along the line joining the two charge from the negative to the positive charge is called a electrical dipole moment. Is called a electric dipole moment. So this thing is called the electrical dipole moment. It's called electric dipole moment. Now remember that there is another type of moment also called the magnetic dipole moment, but here we are referring to electrical dipole moment. So this is called the electrical dipole moment. Now if you look at this, the distance between the two charges is 2L. So O is the center or the center of the distance between minus q and plus q. Distance between minus q and O is taken as L, and the distance between O and positive charge is taken as L. The total distance is 2L and charge on both of them has to be equal, one positive, one negative. So electrical dipole moment P bar, the symbol used for electrical dipole moment is P bar, is given by q into 2L. It's a vector quantity and is directed from the negative to the positive, as you can see over here. So we go to the next part. Now we want to find out the electrical field due to an electrical dipole at a point on its axis, that is the line joining the two charges. So see, here we have got a charge minus q, here we have a charge plus q, O is the center. We have chosen a point P which is at a distance from the center of the dipole O, and that distance OP is R. Distance of P from the positive charge Q is R minus L, as you can see from the geometry of the figure. Distance of minus Q from P is R plus L, and the dipole moment itself is given by P is equal to Q into 2L. So AP is R plus L and BP is R minus L. So we first compute the electrical field due to positive charge, then due to negative charge, and add the two. So see, the electrical field at P due to minus Q is given by K happens to be 1 by 4 pi epsilon naught, Q the charge upon the distance square, and we take it as E1, and it will be directed towards the charge. Electrical field P at due to positive charge will be KQ R minus L the whole square, and that is taken as E2, and it will be directed away from positive Q. Sum total of E1 sum total of energy electrical field at P is E1 plus E2. Now one of them will be negative because there is a change in direction. So we take E is equal to E1 minus E2. As you can see, K q is common, and we have 1 upon r minus L the whole square, 1 upon r plus L the whole square. So you get 4 RL upon this. We have taken LCM, and remember that r plus L the whole square minus r minus L the whole square will be 4 RL. Now this 4 is split as 2 Q2L into R. Now remember Q2L is P, so it will become K, which is 1 by 4 pi epsilon naught 2 P, which is electrical dipole moment, and R divided by R square minus L square the whole square. In case we assume that your R, that is the distance of the center of the dipole to the point P, is much larger compared to the distance L, we can remove the value of L, and then it becomes this way. Now remember, if you substitute the value of K, this is the electrical field at the axis of an electrical dipole. Going further, we look at the electrical field due to an electrical dipole at the perpendicular bisector. So first we have an electrical dipole minus Q plus Q. O is the center, P is a point on the bisector. It is at a distance r from the center of the electrical dipole, perpendicular distance. So the distance AP is root of L square plus R square. Distance BP is R square plus L square, root of R square plus L square. Electrical field at P due to positive charge will go away from it along the line BP. Electrical field at P due to minus Q will be along the line AP and directed towards the point Q. Both will be of equal magnitude because the distance is same, charge is same. Now that electrical field we resolve it along perpendicular and horizontal thing. You will see that E sin theta and E sin theta will cancel each other because the value of E for both the electrical fields are same. So the net electrical field at P will turn out to be 2E cos theta. Moving further, we will say that E is Q upon R square plus L square the whole square. So the root and square will go, you will get this. Cos theta, if you say, is adjacent side upon hypotenuse, will come down to this. So 2E cos theta, we put the value and we will get 2E cos theta as K Q 2L R plus L square raised to 3 by 2. Remember, Q into 2L will be P. Thus we will get that the electrical field at P will be K P upon R square plus L square raised to 3 by 2. Here again, if you say R is greater than L, it will be K P upon R cube. Putting the value of K, the value of E will turn out to be this. Now we look at the electrical field at a general point. So see, we have a dipole minus Q plus Q. P is any point near the dipole. Its distance from the center of the dipole is R, and the line joining the center to P makes an angle theta. So dipole moment is Q P, which is 2L into Q. 2L is the distance between Q and minus Q. Now we resolve the value of P into perpendicular and horizontal thing. So we will get P cos theta, which will be directed along the axis, and P sin theta will be perpendicular to it. So electrical field at P will have two values, one along P and the other along P sin theta. The direction of this P is wrong. It should incidentally be like this. P sin theta should be this way. Okay, so this should be the value of P. So P sin theta would be this way, P cos theta would be this way. So there will be two electrical fields at P, one due to P cos theta and one due to P sin theta. So first thing we resolved it, and the next we do is we take the E1 is the electrical field due to P cos theta, E2 is the electrical field due to P sin theta. So notice the direction, it is opposite to the dipole moment. Here again there is a correction, this is in this, it is directed this way. So E2 is due to P sin theta, E1 is due to P cos theta. So as per the formula we learned just a while ago, E1 will be k2p cos theta by r cube, E2 will be kp sin theta. Notice there is no 2 upon r cube. Since they are vectors, E will be equal to E1 plus E2. So E will be equal to E1 dot the whole square plus E2 dot the whole square. So tan psi will be equal to E1 upon E2. Psi is the angle between the resultant E and E1. Putting the value, you get that tan psi will be equal to tan theta. So we further simplify. Yeah. So here we substitute the value of E1 and E2. Notice that k, p, r cube are common. We can remove outside the radical sign. So we will get kp upon r cube 4 sin square theta plus 4 cos square theta plus sin square theta. Sin square is written as 1 minus cos square, and ultimately we get this value. Additionally, we put the angle psi is equal to tan inverse tan theta. Theta is the angle between the made by the line joining the center to the point, and psi is the angle the resultant E makes with E1 at point P. So we go to the next part of it, and here we look at the torque acting on an electrical dipole placed in a uniform electrical field. Last time we know what is a uniform electrical field. So all electrical field lines are parallel. The electrical dipole itself is made up of two charges, minus q and plus q. They are separated by a distance 2l, and they are placed in an external electrical field capital E, such that the dipole itself is making an angle theta with E. So the force acting on positive charge will be Fq into E. Force acting on negative charge will also be Fq into E, but it will be in the opposite direction. So here we have a system of two opposite forces parallel to each other and having same magnitude. So they will constitute a torque, in the sense they will tend to turn the dipole, here in this case, in a clockwise direction. Now the magnitude of the torque is given as force into distance between the two forces. Distance between the two forces is 2l sin theta. So this looks like this. So the force due to the positive charge is given, force due to negative charge is, the magnitude is same but they are in opposite direction. The two forces are parallel to each other and opposite in direction, so they constitute a torque. The perpendicular distance between the two forces is 2l sin theta. So tau is given by force into perpendicular distance. So tau will be equal to QE, that is the force, into 2l sin theta. Rearranging the term, Q into 2l will become the dipole moment, E is the electrical field, into sin theta. From vector algebra we know that this is tau is a vector, will be P cross E. So in today's lecture we have seen about electrical dipole. In the next case in electrostatics we will look at continuous charge distribution and the electrical field arising due to that. Thank you for joining, and please do subscribe and share my video. Thank you all.